Okay, welcome to the second talk this afternoon. It's a pleasure to welcome Professor Jacques Tilouine, who will tell us about integral period relations, congruence numbers, and special L value.
Thank you very much for the introduction. So remind you that we are defining automorphic periods. So for GL2Q, we defined some coherent period, but we won't use that much. And we define the Manin periods. So this I call, so here this is Fourier integral structure, coherent cohomology integral structure. Here it is Fourier integral structure and Betti plus minus integral structure. So for totally real fields, we don't care about that. We have omega f epsilon. So epsilon is a character of O2 of F tensor R over SO2 of F tensor R. And so we have these these periods. For then we are talking about GLN over F. So F is either totally real or CM. So we were, and so in that case, so again, this is periods of the type Fourier-Betti, epsilon part of Betti, and here it will be Whittaker, epsilon part of Betti. In the real case, there is an epsilon. In the CM case, there is no epsilon. So, so we are defining now these periods. So omega pi, Whittaker, Betti, epsilon, bottom, and omega pi, Whittaker, Betti, epsilon, top. So what are these periods? So they will belong to C cross over O cross. So for that, you have to introduce locally symmetric space. So G is the restriction of scalars from F to Q of GLN. So Y will be YQ, GQ divided under GA over G infinity, A infinity, U. U is compact open inside GF, finite part of the Adels. And so as I said last time, U will be soon the Mira-Horic compact open group of level something. Soon it will be Mira-Horic, but for the moment it does not need. So we consider the cuspidal cohomology of Y with coefficients in V lambda of some rings. So it could be O or for us O or C. And so as I said last time, so there are numbers associated to Y. So first of all, of course, there is a dimension of this variety. This variety is a real manifold, okay, a real manifold of real dimension D. And there is a bottom degree and a top degree. So these index are like that. You have 0, you have the dimension, you have the middle, so D over 2, and you have these numbers B and T, and the length here is L0. L0 is the Harish-Chandra defect of the group G. So this is the rank of the group G infinity, which means G of F infinity of Q of R, sorry. The rank of G of R minus the rank of the maximal compact times center. So you know when there is a Shimura variety, this is 0, but here in general it is not 0. So maybe I give some table which would be nice to keep in mind for all the talks. Well, anyway, I write it here. So the values of L0, B, T, and D for GLN-F. So I take first n equal to F totally real. N equal to F imaginary quadratic. N greater than 2 F equal Q. N greater than 2 F imaginary quadratic. And so, as I said, in that case, there is a Shimura variety, so there is no Harish-Chandra defect. Here, there is a Harish-Chandra defect. Here, of course, there is. I can give you the value, but we don't care so much. N minus 1 minus integral part of n over 2. In the imaginary quadratic case, I want also u to 1. Here, of course, so this is n minus 1. So here it's n minus 1 over 2. Here it's n plus 1 over 2 minus 1. Let me see. Yes, and the dimension. So the dimension here is the degree of the field. No, sorry, twice, because I consider the real dimension, okay? The real dimension. So here it is 3. This is the so-called Bianchi variety, manifold, I don't know. Here it's n plus 1 over 2 minus 1. Here it's n squared minus 1. So for U21, there is no defect because this is the Picard surface, which is a Shimura variety. So there is no defect. And the degree is 2 and dimension is 4. Here, well, this number I call D. So D, as I said, the difference is 0. L0 is 0. This is the difference of these numbers. So here it's 1 and 2, difference is 1. And here you don't care. We don't care. Some integer. Well, I can give you the formula, but well, anyway, some numbers. Well, you know, the sum is equal to, oh yeah, and you have always bottom plus top equal D because they are symmetric with respect to the center. And so in particular, well, okay, so there is a remark which I learned in the paper of Raghuram, and that's very important. This number is the same as this number. This is called a numerical coincidence. So the top dimension for imaginary quadratic coincides with the dimension for the variety. So you see, you consider the variety for GLN-Q and the variety for GLN-F imaginary quadratic. So the top cuspidal cohomology is equal to the dimension of this variety. That's very important for us. That's a fact. Okay, these numbers are equal. And so let's give the examples which are important for us. GL3 over Q. So you get dimension 5, bottom equal 2, and top equal 3. GL3 of imaginary quadratic. Dimension is 8, bottom is 3, and top is 5. So difference is 2, sum is dimension. And for U21, so dimension is 4, so D is 4, and we are considering the middle, so-called middle degree cohomology, so degree 2. Okay, so that's the table, of course, so L0 is 1, and L0 is 2 here, of course, and L0 is 0. Okay, so that's the kind of variety we are considering. For any level, it is always the same, but as I said, we are interested in a specific level because of a multiplicity 1 property of the Mirahorik. Okay, so which is precisely the formula which I wrote last time already, that in the case of the Mirahorik group, of level n, which is equal to the analytic conductor of our cuspidal representation pi, we know that the invariants are one-dimensional. Okay, you take pi on hi, so I between h cuspidal, between p and okay, d lambda c. So we take such a pi, then pi f fixed by u mirroric of level n, where n is the conductor of pi, has dimension 1. So you can pick an automorphic form, well, some phi f inside this thing. It's well defined up to scalar. And as I said, because we know that there is a Whittaker model, we can fix this choice of a vector here by imposing that its Whittaker transform is a function which takes value 1 at 1. So this is what we impose, and this fixes exactly one Whittaker function. And so our first module will be O phi f, so maybe this is phi f 0, because we fixed it. So this is L1. Then we need to define a basis of L2. So what is L2? Then we take the Betti cohomology. Essential vector. No, it does not have this property. This is what I impose. I mean, yeah. No, but I impose that it is 1. So it's fixed. Okay, so this is L1. For L2, we consider the, okay, now for L2, you have to be careful, as I explained. Okay, so now I have to quote a theorem of Borel-Wallach about the dimension of the pi f part. So we are interested in the, so this is a Hecker module, and so you can consider the part of this Hecker module on which Hecker acts as on. So we have this Hecker module, hi y v lambda o, and we take the part on which Hecker acts as on pi f u, hi cuspidal. And this module is, as explained by Raghuram, this has torsion, but all the notions I am defining don't see the torsion. And that's a weakness of these notions. So these periods and the congruence number that I am about to define don't see the torsion, which is nice because we kill the torsion, but we lose something actually. So we don't care about torsion, we go modulo torsion. We have some free O module of finite rank with action of Hecker, which is given by this. But unfortunately, the dimension, so in the totally real case, you can even ask for a part, well, of course, we assume that P is odd and O is p-adic. So we can take the epsilon part in the totally real case, but still, this is not of dimension 1. This is not of rank 1. The rank is known, the rank, the O rank, if you like. This is free of a finite rank over O, and this rank is the following number, L0, I minus bottom B, I minus bottom, which is 1 for bottom and top, because T minus B is L0. Okay? So this is 1 only if I is B or T. If and only if. So this is why it is much easier for us to study the bottom and the top part of the cohomology. And so that's what we do. And so, this module, if we take bottom or top, is free of rank 1. So that will be our L2. L2 will be this thing. H, so I is bottom or top. HI, Y, so cuspidal intersection Betty, V lambda O, epsilon, pi, F, U. Of course, here we need to take the Mirahoric group to get the rank 1. And so this is O delta 2, which we should call O delta 2, Betty, epsilon, and I bottom or top. Okay. And now we use our formalism. Okay, now we need to fix also iota, the isomorphism between L1 tensor C and L2 tensor C. So something which is called the Eichler-Shimura isomorphism, part of it, because it's rank 1. Okay. So of course, it should be called iota epsilon I. There is no epsilon if the field is CM, but there is an epsilon if the field is real. So I try to keep this. I will. Yeah, okay, so to define this, we will send pi f fixed by u to, okay, so now we need to quote the famous Borel-Wallach theorem, which is actually a theorem of Matsushima-Shimura, which has been reformulated in the adelic language by Borel-Wallach. But yeah, so basically it's Matsushima-Shimura in the 60s, plus Borel-Wallach, plus Harder and Franke, if you like. But we will focus on the cuspidal part because Borel-Wallach treats the compact case, and we need non-compact case, but we need only the cuspidal part. So kind of contained in Borel-Wallach. So this is that the cohomology HI cuspidal Y V lambda C can be decomposed as sum of pi prime F fixed by U tensor HI G K infinity V lambda C tensor pi infinity, well, so-called pi infinity K infinity, over, so pi prime, over all the pi primes F, such that pi prime F tensor pi infinity is cuspidal automorphic, is automorphic cuspidal, where pi infinity, the infinitesimal character of pi infinity, pi prime infinity, is the infinitesimal character of V lambda dual. So you have this decomposition. So for us, we fix a pi. So pi is one of these pi primes. Pi is one of them. So this is for us one-dimensional. So the map is simply, so for I equal bottom or top, this is one-dimensional. And so we need to fix a basis of this. And this is a rather delicate thing, but so we will fix, there is a way, which I don't want to explain now, there is a way to fix a basis. Of course, there is an epsilon somewhere. There is a way to fix a basis of this one-dimensional, so bottom or top, okay? Epsilon bottom or top. This is dimension 1. And so there is a way to fix a basis, let's say a canonical basis. There is a choice of Whittaker functions using Barnes formulas. You can choose canonically a Whittaker function at infinity, and you can choose a canonical vector. When I say canonical, it means up to a unit in O. Okay, so this is well defined as a basis, even okay, up to O cross. So then, of course, the map the map that we are studying is nothing but O phi F0 goes to this, to HI cuspidal Y B lambda C epsilon pi F U. It's given by the formula phi F0 goes to phi F0 tensor pi infinity, all these indexes, but I epsilon. So you just choose a basis, and that's iota. And this is Eichler-Shimura. And so this is what we fix. And so this defines for us periods. So we get these periods, omega pi epsilon, and bottom or top. And okay. Omega pi epsilon bottom and omega pi epsilon top for all epsilon. And if the field is CM, there is no epsilon. So we have these periods. So this has been defined by Eric Urban in his thesis in 1995 in the case of GL2 of an imaginary quadratic field. So in that case, maybe I should have said that there is another interesting case, which is GL2 of imaginary quadratic. So for that, D is 3, L0 is 1, bottom is 1, top is 2. And so you have two periods, omega 1 and omega 2. So Eric Urban defined omega 1 pi and omega 2 pi. There is no epsilon because the field is not real. And more generally, you have all these periods. So here you have omega 2 and omega 3. There are no pi. Oh, yeah, there is epsilon. The epsilon is just plus minus because the field is Q. And so you have only two characters, plus and minus. So here you have omega 2 plus minus and omega 3 plus minus. In that case, omega pi. And in that case, you have omega pi 3 and omega pi 5. No, so you have two periods here, 4 periods here, and 2 periods there. And here, you just have, well, here, we will see later. We will see that. But here it will be useful to use Whittaker coherent periods. So we have defined many periods, and so that's it. Now we want to define, so now what is the program for today? The program for today is to talk about Hecke algebras, Hecke eigenvalues. So I can write the program. So these are the atoms which we use to define the automorphic periods. You remember that we are trying to define analog of these objects which are very difficult to reach. We want to define analog which are automorphic. And we will use them, we will define them as products of these periods that I defined. Okay, all these periods, we will make some products, and this will define for us these automorphic periods for this motif. Well, for this motif to be. But we don't care that it's a motif. We would care here, but we don't care here. Yeah, okay, so I said Hecke algebras, Hecke eigenvalues, Hecke eigensystems, Galois representations, and congruence numbers. Okay. Well, okay, I said it, it's okay. So we consider some level group U, for instance, the Mirahoric, compact open. And so we can consider the abstract Hecke algebra. So G is the same as before, restriction of scalars from F to Q of GLN. So we have the abstract Hecke algebra outside S. S is a ramification set for U, which means it's a set of primes where UQ not hyperspecial maximal. This is Ram U is the set of primes Q such that UQ is not hyperspecial. So it's a finite set, which I denote by S. So I consider the Hecke algebra outside S. So that will be the tensor product for all primes Q not in S of the spherical Hecke algebras HQ. And the spherical Hecke algebra, as you know, is a Z, G of ZQ under G of QQ over G of ZQ. And it is just, actually, it's a polynomial algebra in T in variables, except that there is a Laurent thing, TQN plus minus 1. So the last one you can invert, the other one you cannot. And so what are these Hecke operators? These are Q, 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 1, 1, 1. I of them, this is TQI. And you take the double class U, well, US, US. Oh, we are local, sorry, we are local. So G of GQ, G of ZQ. Okay, so easy fact. And so we have this abstract Hecke algebra. This is the abstract spherical Hecke algebra. Spherical because we removed the places where it is not spherical. And so we have a tensor product of spherical, so abstract spherical Hecke algebra. And so we fix our pi, which is cuspidal, cohomological, automorphic on G of A, let's say of level U. So if we take pi S fixed by US, this is one-dimensional. So pi outside S, so this is the tensor product of the pi Q for Q not in S, okay? And US is the, U is US times US. So this is hyperspecial, and this is not. And so this is one-dimensional. So the Hecke algebra acts on this, and so this defines, so you have an action of HS, and therefore you have an algebra homomorphism from HS to O that we call theta pi. O, as I said, is a p-adic ring which is sufficiently big to contain the Hecke eigenvalues. And such a homomorphism is called a Hecke eigensystem. Once you have seen O, which comes from theta pi, well, you tensor by O so that it becomes an O algebra homomorphism. Okay? So you have an O algebra homomorphism called Hecke eigensystem. And that's nice, but we actually we want to, so this is p-adic, and here the ramification is supposed not to contain P. So I have to explain exactly what happens at P. I gave you a formula, which is nice, but you can do better at P. So P is there. P is not in S, okay? P has been chosen to be not in S. P is not a ramification prime in my assumption. So it is there, but at P, we make small modification because otherwise it's okay, but everything will be divisible by P, and we want to be as little divisible by P as possible for the Hecke eigenvalues. Otherwise, they are all divisible by P. So we have to modify slightly the Hecke operators at P. There is a trick for that. Yeah, okay. So I explain how we modify the operators at P. So anyway, we will let the Hecke algebra act not only on this one-dimensional space, but on the cohomology. And on the cohomology, we will concentrate only on the bottom and top. So we will have this module. And so the definition of the action of Hecke operators. So a Hecke operator can be viewed as something like a U, T, U, where T, US, T, US, where T can be taken in the torus. The torus T of the finite adels. So we are interested by the action. Sorry, outside S. Yeah. So we are interested at for the behavior at P. So TP is in T of QP, viewed inside this. Okay, and so the whole I won't define the action of T of QP. I will define the action of T of QP intersection the integral matrices. So I will assume that the element, like for instance, something like that, PPP 111, that's perfect. Okay, this is in the torus, but it is integral. Okay, that's the kind of elements we consider. And I want to define the action of these Hecke operators, and that's nice, but we can define that easily. So the usual way is the following: you consider the group U intersection TP U TP minus 1, maybe I call it U of TP, and the group U intersection TP minus 1 U TP, which I call U of TP minus 1. And I consider well, you know, I am a p-adic guy, so this kind of subtleties, you might find it boring, but that's my cup of tea. So if everything is divisible by P, we lose kind of everything. We need to improve that. Yeah, so the construction of the Hecke action. So we want to define the Hecke action of this. So that's as usual. You consider the inclusions. U of TP minus 1 is included into U. U of TP minus 1 is isomorphic by conjugation to U of TP, and this is contained in U. Okay? And so from this diagram, you deduce a diagram of varieties. So you will have Y of U of TP minus 1 goes to Y of U. You will have an isomorphism U of TP, and you will have here U, U, okay, like this. So you have such a diagram. So this is the obvious morphism induced by this inclusion. This is an isomorphism induced by the conjugation, and this is the obvious projection induced by this inclusion here. So you have this diagram of varieties, and it induces a diagram of cohomology. So you will have HI YU V lambda. You take pi 2 upper star goes to HI YU, sorry, UTP minus 1 V lambda goes to hi y u of TP V lambda by 1 lower star. It makes sense because all these morphisms are finite, h, y, u, v lambda over the integers. And so the point is that to define these morphisms, you need to have also a morphism of sheaf. So here it's the obvious one. Here, that's the point. So here you have the conjugation isomorphism. Here you take the map, the following map, from the representation V lambda O to the representation V lambda O. You define V goes to V TP minus 1. And why does this make sense? Because the definition of this right action, so this right action is, let me see. Yeah, this right action by definition is the left action of the inverse. Okay? And so, so this makes sense, okay? Because you can multiply an integral matrix by this integral vector and you get an integral vector. So that's the point. And so what you do now, you have this action, and now what you do is that you notice that V lambda O can be decomposed into so-called weight spaces. So V lambda O, mu, where mu runs in the set of weights. So it is between lambda, I don't know how to write this, maybe like, and W0 lambda. W0 is the longest element of the Wiles group. So you have this decomposition, which is valid over the integers. That's a property of these representations. Okay, that's a fact. This is compatible with the action of the torus, algebraic action of the torus as a group scheme over O. You have such a decomposition. And so you see that the mu's are greater than that. So this means that if you let TP act, for instance, this kind of TP, which disappeared, this kind of TP, it will create mu of TP, which is a power of P. But if you divide by this, you will have one of the eigenspaces here for which the action is a unit. And this becomes optimal. So this is how you modify the definition. So you take W0 lambda minus 1 of TP times the operator U, which I defined by the diagram. So you have this operator. I put a bracket to explain that this is this composition. This composition is the action of the double class. This is this operator, but you modify it by this. Then it is optimal. And so this is the operator which I could call TPI modified. Or you take TPI modified. And then this becomes an optimal action. So this is how we let the P part act. Anyway, so we do that. Sorry? No. This is a scheme theoretic property. This is true. This is true. Absolutely. Over the integers. Over Z. This is true over Z. This is for a torus. You know, you couldn't decompose a module into a sum of simple modules for a group G in general over the integers unless P is sufficiently large. But for a torus, you have that. Okay, so anyway, we modify the action at P. Then we know that there is a Galois, well, without doing this, there is a Galois representation associated to pi. Just recall that because we will need it. So from Galois Q to GLN of O, and which has some specific property. So it is unramified outside S union infinity. And if Q is not in S, the characteristic, well, okay, it's better. Yeah, there is an F. We said there is an F, so it's better to, yeah. As characteristic polynomial, well, as you know, xn minus t v1 xn minus 1 plus minus 1 to the I norm of v to the I minus 1 over 2 x to the n minus I. Oh, yeah, I forget. Yeah, of course, this is a Hecke operator, so I have to apply theta pi. Yeah, times norm of v to the n minus 1 over 2. So this is the formula for the characteristic polynomial. And so that's nice. And in all this work, we assume that the residual representation is absolutely irreducible. In other words, there is a name for that. It means that if you consider this character theta pi with values in O, you reduce it modulo pi. So let's call F the residue field. You consider this composition. You consider the maximal, so you call this maybe theta pi bar. You consider the kernel of this reduction. This is a maximal ideal of the abstract Hecke algebra, and this is called non-Eisenstein. So we are in the non-Eisenstein situation throughout this work. So, contrary to the situation studied by Raghuram, which is the Eisenstein situation. So non-Eisenstein is that, of course, you cannot have any congruence between pi and an Eisenstein series, because otherwise the residual representation would be reducible. And that's exactly what we assume not to be true. Okay, so it's impossible to have this Hecke eigensystem congruent to an Eisenstein Hecke eigensystem, modulo our prime pi. Okay, we have a prime pi. So this never happens. This is our assumption of non-Eisensteinness, okay, because of this absolute irreducibility, because such a representation, Eisenstein, would be reducible. So we are not dealing with Eisenstein congruences. So the Ramanujan congruences modulo 691 is excluded in this work. But we can have congruences, but they will be cuspidal. Okay? Theta pi could be congruent to theta for another cuspidal representation, modulo pi. That's possible, but that is impossible. That's crucial in this work. So basically, we are killing the Eisenstein part of the cohomology. And so, you know, the module which is interesting for us is the following. It is HI, so I is only bottom or top, Y, level Mirahoric, B lambda O, localized at this non-Eisenstein prime viewed as a Hecke algebra module. And so we will introduce a Hecke algebra which acts faithfully on the cohomology, and we denote this Hecke algebra by T. So T is contained, so this is faithful action, okay? So it is the following. You have the abstract Hecke algebra, which maps to here, okay? First of all, it factors through the Hecke algebra acting faithfully on the cohomology, and then we localize at M this Hecke algebra. So it's not trivial, but it's not hard using Borel-Wallach theorem to show that the action of the abstract Hecke algebra on the cohomology factors through well, you just take the image. You just take the image of this abstract Hecke algebra inside the endomorphisms. Okay. And then you localize, and that's T. Well, well, there is maybe something to check, but it is true. So, so you have the localization, if you like. Yeah, so you have this, I should call it M bar because it is here, it is inside the cohomology, but let's call it M. So this is a local. So you see the difference is that this is a huge algebra. It's a polynomial, infinitely many variables, polynomial algebra. But this one is a finite O algebra. So this is a finite. When I say finite, it means of finite rank over O. It's a finite O algebra with torsion, because this cohomology has torsion, but we don't care about that, okay? You, just like you replace the cohomology by modulo torsion, same for T. T has torsion, but T bar is T modulo torsion, and it's okay. It's as good as T for us, but we lose something. Anyway, that's what we do. We don't care about the torsion, neither here nor there. At some point, we will have to pay for that. So we will never, well, we will very rarely see the Selmer group itself. We will see the congruence numbers, and the difference between the congruence number and the Selmer group is related to the torsion. Well, yeah, and that may happen. So congruence numbers, periods, don't see torsion. Okay? But Selmer group does. So the automorphic periods may not be exactly the best ones. They are maybe not the motivic ones. It's up to an interesting number that we defined with Eric Urban, and we call it the Wiles defect. There is some integer called the Wiles defect, which expresses the difference between automorphic periods and motivic periods. I don't want to say that Wiles has defect, just like Harishchandra. It is fully general. It is for over any it's a commutative algebra object. You know, you will see when I do the formalism of yeah, I don't know whether I will have time to explain it, but it's I can. I will be able to explain exactly what it is. Okay, so I said I wanted to define Hecke algebras, Hecke eigensystem, Galois representations, congruence numbers. Why not? I could define, yeah, okay. Okay, congruence numbers. So we have this algebra T, but as I said, we go modulo torsion. So it's a finite, flat O algebra because I killed the torsion. So we take such a finite, flat O algebra, And I remind you that the field of fractions of this is E. Okay, track O is the field E, which is a p-adic field, sufficiently big, and so we tensor this ring by the field of fractions. So this means I tensor by E, and we defined the Hecke algebra using only unramified Hecke operators. And so, because of that, this finite algebra is actually semi-simple. Okay, this is not the case if you include the bad Hecke operators, but here this is semi-simple. So we had a homomorphism. Yeah, this is something which is not hard to check, but has to be checked, but I won't check it, which is that this homomorphism, which I defined, okay, factors through this quotient. Okay, it is a fact, and that comes from Borel-Wallach. Okay, so now I will consider this homomorphism of O algebras, and this is still the same. You take a Hecke operator and you consider the Hecke eigenvalue. So the value here, theta pi of t, is just the action of t on vectors belonging to pi s fixed by us, this one-dimensional vector space. This is given by theta pi of t v. Okay, but this action factors through this Hecke algebra, which is defined to act faithfully on the cohomology. Okay, this one acts faithfully on the cohomology, and it is very small. It is contained in the endomorphisms of the cohomology, if you like. Actually localized, but anyway. So you know, this is a finite rank O module. This is not large. You can show that this is a finite rank O module, the whole cohomology. So we are talking about a finite O algebra. Finite means finite rank, okay? And so we have this map, as I said, because of Borel-Wallach. It's a corollary of Borel-Wallach description of the cohomology in terms of the representations. Okay, so we have that. And so, so we have this data. I tensor it by the identity. So I have this. And as I said, because this algebra is semi-simple, I can split this homomorphism. So I split it, and I get TE equal E times something else, which I denote by T prime E, another semi-simple E algebra. You know, if E is a sufficiently big field, actually this algebra is just E times E times E times E times E, and here we take the rest. And what are these E's? They are the theta pi primes. Okay? So this projection, the first projection is theta pi, and the other projections are given by the other cusp forms, which are congruent to the original form pi, because we have localized. I remind you that T is the Hecke algebra localized at M. So basically, the number of copies is the number of cuspidal, cohomological, automorphic representations pi primes, which are congruent to pi modulo pi, pi like this. Okay, so this algebra is not mysterious. It's just a product of copies of E if E is sufficiently large. Okay, okay, that's the situation over E. But now let's see what happens over O. So we have, as I said, this algebra has no torsion. So it is contained in here. Okay, and so we have the first projection to O. And let's denote by T prime the other projection. So this is the image of this integral thing in here. Okay? So it's the two projections are surjective, of course. by definition, this is the surjective image of T bar. And now, what is the congruence module? Or the congruence number. So, well, you can define it in the following way. You take eta pi inside O to be, so you have two projections here, two projections. The first projection, PR1, is theta pi, and the second projection is, I don't know. Well, you see, I can use notations as follows. There are two idempotents here. You have 1, 0 and 0, 1. And the sum is the unit here, okay? So this idempotent, I denote it by 1 pi. 1 pi is the first idempotent. This is the projection to E. So this is PR1, this is theta pi, this is multiplication by 1 pi. Okay, multiplication by 1 pi is this. And the other one I denote by 1 t prime. Multiplication by 1 t prime, okay? So, so I want to define this thing inside O. So you do the following. You take, how do I say? You take E times O, so I don't know how, 1 pi of TE, okay, intersection, no, just a second, I want to say it correctly. No, it's not 1 pi of TE, it's want to be too fast. Yeah, that's correct. You take T bar intersection 1 pi of TE. So what do we get? We get inside, so this is a one-dimensional E vector space. We take the intersection with this lattice. We get a lattice in E. This lattice is eta pi inside O. Why eta pi is contained in O? Because eta pi is an element in here for which, if you apply theta pi, you get itself. And theta pi maps, written somewhere, theta pi maps T to O. Okay? This element belongs to T bar. So the image is integral. But this element is a 1 pi, and theta pi of 1 pi is 1. So we have this formula. And so, so we have an ideal. It's an ideal, I call it a number in O. So if you want another description, which is maybe more understandable, you have this morphism to O, which is theta pi. And you have the other morphism to T prime, which is the other, which is multiplication by 1 T prime. And as I explained, in characteristic 0, so if you remain over O, this corresponds to pi, this corresponds to the other representations pi prime. They are completely different from pi. But if you reduce modulo eta pi, then you will have an ideal here such that if you reduce modulo this ideal, these two rings are isomorphic and this diagram commutes. So eta pi is, so this is the largest quotient of O for which such a diagram commutes. Okay? There are many, many ways to describe the congruent ideal or number. So you see here, I am describing it as a, how do you say that? Is it a push out? So this is the largest quotient for which this diagram factors through T prime, okay, through this map, such that this factors through this. Yeah. Okay. So that's the congruence. So this congruence number, we call it the Hecke congruence number. Hecke congruence number eta pi. Now we will define, so now we fix a module. M is a finite flat O module. And we consider with action of T bar. So it's a module over the Hecke algebra, which is finite flat over O. Now we will define the M congruence number. That's another one, but very similar. And sometimes they are equal. So which will be denoted by eta pi of M. So how do you define that? Oh, yeah, okay. I make an assumption to define it, namely that, okay, so I will explain the assumption now. It is not absolutely necessary, but it makes life much simpler. Namely, you see, something I don't assume is that M is free over the Hecke algebra. If it is free over the Hecke algebra, it's just the same as before, but it may not be free. This is free over O, but maybe not free over the Hecke algebra. But we assume it is rank 1 over the Hecke algebra in the following sense, namely that if we apply 1 pi to M, to ME, so ME is, we extend the scalars to E over O, and we apply 1 pi, we assume that dimension over E of this is 1. This is our assumption. But we don't need to assume, again, M may not be free of rank 1, of course, over T bar. May not be free over T bar. But anyway, we assume that. So you see, we have M, we tensor by E. So this is a module over TE. And in TE, we have idempotents. We have the idempotent 1 pi, and we have the idempotent 1 T prime. Okay? And so we can use them to decompose this into 2 parts, 1 pi ME plus 1 T prime ME. And as I said, this is one-dimensional. This is maybe not, okay, of course. Okay. And so we now from this, we do exactly the same construction. So we consider 2 interesting modules. One is denoted by M upper pi, and this is the image by the idempotent 1 pi of M. And you have to be very careful that this is not contained in M, because the idempotent 1 pi is not integral. This idempotent makes sense when you tensor by E, but it is not an element of T. 1 pi is not an element of the integral T. It is an element of TE. And there is a denominator. This denominator, by the way, is eta pi. If you want another definition of eta pi, it is that eta pi is the denominator of 1 pi with respect to t bar, which is the integral structure that we pick inside TE. Inside this E algebra, there is an O algebra, so there is a notion of denominator for an element in this E algebra, and that exercise, it is also eta pi. Okay, but again, this thing may not be integral because 1 pi is not integral. Okay, so this is one thing. There is another thing which is integral, namely the intersection of m with 1 pi of me. And obviously, this is contained in m upper pi. And the quotient is the congruence module, but as I said, m pi so we consider m pi over m pi, but as I explained, this is free of rank 1 over O. So you can identify this module with O. If you identify this module with O, then you identify this module with something which is an ideal called eta pi of m. That's the definition of eta pi of m. And you always have, by definition, the divisibility eta pi of m divides eta pi. But unfortunately, it may not be an equality. But it is an equality if m is free over the Hecke algebra, of course. So in the case where m is free over the Hecke algebra, you have equality. I should stop here, no? It's 1 hour, no? Yeah, yeah, thank you. But yeah, but it's 1 hour, no? All right. So I continue Thursday. So next time, because now we have the congruence numbers, so we will be able to state the theorems calculating the congruence numbers as special values of L functions divided by the automorphic periods, which I haven't yet defined, but soon. Now we have everything to define them. So we will have this kind of formulas in many cases. I will explain briefly the proof. The proof is not hard, actually. But yeah. It relies on something analytic, which is called the Lapide-Mao, well, the Rankin-Selberg formula, or more generally, the Lapide-Mao formula, which is a conjecture, but it is proven in some cases. And the Rankin-Selberg formula, you need to relate the adjoint L value to a Peterson product. If you do that, you are good. This becomes very easy because I will explain the formalism of congruence numbers, and there is a formula computing congruence numbers as basically Poincaré duality or Poincaré pairing of elements, and this Poincaré pairing corresponds to Peterson product. So if you can relate this to Peterson product, you are good to relate this to congruence number once you divide by periods. So that will be, this is not the hard part, okay? That will be the starting point, starting point. Okay.